We're going to work through a fairly typical annual growth rate example. Suppose we start with $9,200 in an account that is earning 8% annually. If it's earning 8% annually, then the base of the exponential function is 1 plus 0.08 divided by 1, or 1 plus 0.08. So 1.08 is our base, and its exponent, x, are years. We want to know in how many years our account of $9,200 is going to grow to $15,000. As in solving many equations, we're trying to undo all the arithmetic to get at the variable, so we want to work from the outside in. So the most outside operation is multiplying by 9,200. The inverse of multiplying is division, so I'm going to divide both sides by 9,200, and that fraction reduces to 75 over 46. So 75 over 46 is then equal to my base of 1.08 to the x. We want to undo the exponential function. So we are going to plug both sides of the equation into log base 1.08, because log base 1.08 will undo exponential base 1.08. So on the left side, the fraction 75 over 46 gets plugged into the function log base 1.08. Same with the right hand side, but on the right hand side, the log base 1.08 cancels the exponential base 1.08, giving me just x. So x is equal to the value log base 1.08 of 75 over 46. That is a number. It doesn't look like an obvious number to us right now, but log base 1.08 of 75/46 is the exact value that is equal to our number of years. We can see from the graph that it's a little bit more than 5. It looks like it's somewhere between 6 and 7 years. Most scientific calculators have a natural log button. Excel also has a natural log function, so we could convert our log base 1.08 into natural log. So hitting the ln button on the calculator and then putting in the input 75/46, dividing that by ln of 1.08. I am using the change of base formula for logs that we talked about in the earlier video. And so log base 1.08 of 75/46 is equal to natural log of 75/46 divided by natural log of 1.08. Typing that on the calculator, we get approximately 6.352 years. As we saw from the graph, it was somewhere between 6 years and 7 years. My account will have $15,000. We could work that same problem in an equivalent manner by, at the very beginning, converting the base 1.08 of the exponential function to base e. Remember the change of base formula for exponential functions. If I change the base, there's a new coefficient in the exponent, which is log of the new base with the old base plugged into it. So in this case, my $9,200 stays my leading coefficient, but if I want the base to now be e, it will be raised to x times natural log of 1.08. Notice 1.08 was the old base. From there, just do the same algebra that we did before. Work from the outside, so divide by 9,200. That still reduces to 75 over 46, but now that is equal to e raised to the x times natural log of 1.08. My base is now e. It's no longer 1.08. So the inverse function for e has that notation, natural log, ln. So plug both sides of the equation into the function natural log. So on the left, 75/46 gets plugged into natural log, the inverse function of exponential base e. And on the right, I take e to its exponent and plug it into natural log. The job of natural log is to cancel exponential base e. So on the right-hand side, I no longer have an exponential function. I have x times natural log of 1.08. So to solve for x, divide, because division is the inverse function of multiplying. And when I divide both sides by natural log of 1.08 to get x by itself, look, I have the same thing I had before when I got to the very end of the problem and used the change of base formula for logs. If I'm changing into natural log, in the numerator we had natural log of 75/46 divided by natural log of 1.08. And again, that's approximately 6.352 years. You read that a certain make of car depreciates in value exponentially from the moment it is driven off the lot. This car's initial value was $47,000. In 3 years, it is estimated to be worth $33,500. Find the formula for the model which patterns the decrease in this car's worth using the information provided. And then use your model to find how much the car will be worth in 8 years. Does the model predict that the car will ever be worth $0? Why do you answer as you do? In the problem, we are actually not told a specific base, we're just told that it depreciates exponentially, so we might as well assume it's continual exponential decay. From the moment it's driven off the lot, the worth starts to decay, so we might as well assume continuous exponential. So we're going to use base E. We know that initially the car was worth $47,000, so that is always my leading coefficient for an exponential function. For an exponential function, when you plug in 0, anything to the 0 power is 1, so the leading coefficient should be the initial value. So 47,000 times e to the 3x needs to equal 33,500. We have 3x in the exponent because we don't know the rate, but we're told in 3 years it's going to be worth 33,500. So the 3 is actually for years. So I have years times my unknown rate. We're trying to solve for the rate. As before, work from the outside in. So the most outside operation is multiplying by that 47,000. So divide both sides by 47,000. That fraction reduces to 335 in the numerator, 470 in the denominator. So e to the 3x is equal to this fraction. I want to get at the variable, which is in an exponent on a base of e. So the natural log function is the inverse for exponential base e. Plug e to 3x into its inverse function. Whatever I do to one side, I have to do the same thing to the other side. So the 335 over 470 also gets plugged in to the natural log function. We're basically finished at this point. The natural log cancels out base e, giving me 3x, and 3x is then equal to the number ln of 335 over 470. To get x completely by itself, divide by 3. So x is equal to exactly 1/3 times natural log of 335 divided by 470. If I type that in my calculator, I get negative 0.1128, or approximately 11.28% depreciation per year. I guess if I actually say the word depreciation, I don't need the negative, but the value is negative because we have a decreasing exponential function. So instead of the exponent being positive and the value increasing, the exponent is negative and my value is decreasing. Remember, e is approximately 2.718, so my base is bigger than 1, so to depreciate, the exponent needs to be negative. So our model is the initial value of $47,000 times e to the negative 0.1128 times my input x, and x is now the years. If I want to know what the car is worth in 8 years, then put 8 in for x and do the calculation on your calculator, and you get approximately $19,062.97. Again, it's just an estimate, so you could round up to $19,063 if you wanted to. And the car will never be worth zero. One, it makes sense that the car is never going to actually be worth zero. It's probably going to be worth something to somebody. Also, exponential functions never reach a value of zero. They have the x-axis as a horizontal asymptote. It is not possible to find a value for x that would actually make the function equal to zero. Let's practice again with a general equation. I have 40,012 equal to 4 times base 10 raised to the x minus 3 power, and then 12 added to that exponential expression. Start from the outside in, and the most outside operation is adding that 12. The inverse of adding is subtracting, so subtract 12 from both sides, and I get 40,000 equals 4 times 10 to the x minus 3. Then keep working from the outside in, divide by 4, and then 40,000 divided by 4 will equal our basic exponential function with base 10 raised to the x minus 3. In this case, 10,000 is a nice clean power of 10. So for this particular equation, it's helpful to rewrite 10,000 as 10 to the 4th. And then if you stare at that, 10 to the 4th equals 10 to the x minus 3, we could just use common sense and realize, hey, the exponents have to be the same, and we could convert our exponential function down to a simple linear function. 4 has to equal x minus 3. Hence, to solve for x, add 3 to both sides, x has to be 7. Hopefully common sense will be catching on, and if you see common sense, you can kind of tell what an equation's solution is. It's okay to reason it out that way.
Let us look at a doubling time problem for an account in which interest is compounded quarterly. If interest is compounded quarterly, it means that every quarter, or every 1/4 of a year, the interest that an account earns is added into the account, and then that interest also earns interest as well as the initial amount of money for the following quarter. But the financial institution does not agree to give the full 2.25%, or whatever the rate is, every quarter. Instead, they award the account 1/4 of the yearly interest rate every quarter. So if you were Carl Cautious and you were investing $7,250 in a certificate of deposit that is earning a yearly rate of 2.25%, the formula that would calculate how much money is in the account as the quarters went by would be $7,250 as my initial amount, multiplied by the base of 1 plus 0.0225 divided by 4. So again, that's the yearly rate written as a decimal divided by 4 because we're compounding quarterly. And that base is raised to the power 4 times t. 4 is the number of compoundings per year, and t is the amount of time in years. If we are interested in the doubling time, it means we're interested in how long it will take for the account to double in size. So for $7,250 as our starting amount, twice $7,250 is going to be $14,500. So to solve our doubling time equation, our first step will be to divide both sides by the leading coefficient of 7,250. And no surprise, when we divide, we get the number 2 on the left-hand side of the equation, because we were trying to find for when the amount was going to be doubled. So now we're trying to get at the variable. We're trying to solve for the variable, which is in the exponent. So we need to undo this exponential function. I need the inverse of this exponential function. At this point, it might be helpful to rewrite the base as a single value. So 1 plus 0.0225 divided by 4 is 1.005625. And so that is our base, and it is being raised to the 4t power. So we are going to use an inverse function for this exponential function, and that inverse function will be log of base 1.005625. So what we are doing then is we are taking both sides of the equation, because whatever you do to one side, you have to do the same thing to the other side to keep your equation balanced. So 2 is going to get plugged into the function log base 1.005625. And the right-hand side, which is the exponential function, is also going to get plugged into that log function. And on the right-hand side, the log function is going to cancel the exponential function. On the left-hand side, log of base 1.005625 with 2 plugged in is some number. So with both sides now plugged into the log function, on the right-hand side, the function cleans up to just be 4t, which was the input of the exponential function that got canceled by its inverse function of log base 1.005625. On the left-hand side, again, we have this number, log base 1.005625 with 2 plugged into it. Now my calculator does not have a log base 1.005625 button, so I'm going to need to use the change of base formula and use either natural log or log base 10, because my calculator has both of those log functions programmed in the calculator. I'm going to choose to use natural log. So I'm using the change of base formula. I'm changing log base 1.005625 into natural log. So the change of base formula says take the new log of the input, so 2 is my input, so natural log of 2, and divide by the new log with the old base plugged in. So in the denominator should be natural log of 1.005625. And again, if I type all that in on my calculator, that is some numerical value. To actually get the time then, I need to divide that value by 4, and then that will solve finally for the time. If we carefully type all of that into the calculator, we can see that it turns out to be 30.893 years. So Carl Cautious is going to have to also be patient as he waits for his account to double in value when it's earning only 2.25% interest. So Carl may want to be a little less cautious and put some money to work in the stock market, but at least he knows 31 years from now he will have twice as much money as he had when he started. As noted, it would take a pretty long time for an account earning only 2.25% interest to grow, so you might find quick results if you create a stream of deposits. Suppose you invest $175 each month into an index fund, and in general, the index fund is earning 8% annually. Let's find how long it would take for the account to grow to $42,500. This is called a stream of deposits, and we are going to just use the formula for a stream of deposits. Where this formula is derived is a whole nother lesson. We're going to focus on how to solve the equation from the point of view of how to solve exponential equations. But if we were depositing $175 each month into an account earning an annual 8% interest, the stream of deposits formula is shown below, where n is the total number of months. So we're going to solve for the total number of months that it would take for the account to grow to $42,500. So we have our equation actually set up. We could clean up some of these values, but I like to try to keep things in exact form and round at the very end, just to make sure that I'm getting as exact an answer as possible. But if you need to clean up some of the values just to kind of help handle the formula, you are welcome to do that when you practice this problem and you rework it. So first, I would multiply both sides of the equation by the denominator of the fraction that we have. So I would multiply both sides by 1.08 raised to the 112 minus 1. So notice on the left-hand side, I have parentheses indicating I'm multiplying the 42,500 by that entire denominator. And then when the right-hand side gets multiplied by that denominator, it gets canceled. So I'm left just with the numerator. Then, again, I'm trying to whittle things away from the variables. So the next thing I'm going to whittle away is the 175 that's being multiplied, and the 1.08 to the 112 that is multiplying the expression that has the variable in it. So divide both sides by 175 times 1.08 to the 12. And now we've whittled things away even further, so we're down to just two terms where one of them involves my variable. The next step is to whittle away the subtracting 1. So adding is the inverse operation of subtraction. So I add 1 to both sides, and on the left I now have 1 added to the expression I had, and on the right hand side the minus 1 is gone, and I now just have the one term on the right hand side, 1.08 to the n divided by 12 power. So again, we're trying to solve for that n. So I'm at this point it's in an exponent, so I am going to need to use a log function that will cancel my exponential function. So trying to solve for our variable, the variable is in an exponent. The base of that exponent is 1.08. So I need to take both sides of the equation and plug it in as the input to a log base 1.08 function. So on the left-hand side, that whole big expression is getting plugged into the function log base 1.08. And on the right-hand side, my exponential function is also getting plugged into log of base 1.08. And the job of the log function is to cancel the exponential function. So we can see that the log function and the exponential function cancel each other out, leaving me with the input of the exponential function, the n divided by 12. That was what was plugged into the exponential function. It is what you have left after the log function and the exponential function cancel. And on the left-hand side, I have log base 1.08 of that whole number that was forming the bulk of our equation. And I have almost solved for n. I'm down to only needing to undo one last little step. Lastly, to get n all by itself is to multiply both sides by 12, and multiplying by 12 cancels the division of 12. On the left-hand side, I now have the big log expression multiplied by 12, and on the right-hand side, I have finally solved for n. Now, my calculator does not have a log base 1.08 button. It does have a natural log button, and it has a log base 10 button. So I would need to use either one of those and my change of base formula. So again, the change of base formula, if you change a log base to a different base, in the numerator you have the new log with the input plugged into it, and then you divide that by the new log with the old base plugged into it. So in our case, I will have in the numerator natural log of that whole big expression divided by natural log of the old base, 1.08. I have carefully typed that entire expression, including the multiplication by 12, into a Texas Instruments graphing calculator in classic mode, and I see that I get 146.11 months. So it's going to take about 146 months. If I divide that by 12, I can see that it's slightly more than 12 years. It's 12 years and 2 months. As mentioned, if you wanted to clean up some of the numbers as you went along, the big number that is plugged into the log in the numerator is approximately 2.5525609. So instead, if you wanted to type it in the calculator by first cleaning up that expression by little, doing each step, you can do that. Just again, be careful of all the steps. And you can see that when I did clean up the numbers, I'm still getting 146 months, and 146 months is 12 years and 2 months. So certainly less time to build up quite a bit of equity. And if you're just putting $175 away each month, you're probably not even missing the $175. Exponential functions are so helpful because a lot of things grow exponentially, including a lot of animals out in our world. So recent reports indicate that a fish called a snakehead fish is invading waters in the southeast United States. In a certain stream, it is estimated that there are now 150 of these fish. A year ago, the estimate was 30 fish. If it is assumed the number of fish is growing exponentially, find the initial number of fish 3 years ago when reports first surfaced. Also find the estimated number of fish that there will be in 3 more years. Since we know the population of fish is growing exponentially, we know that our basic function formula is y equals the leading coefficient is the initial amount of fish times e to the kx. We could use any base because any base can be rewritten as any other base, but choosing e is usually a good idea because in the long run it'll make our work more clean. So we're going to use e as a base. So we know 1 year ago there were 30 fish, so the output or the y value should be 30 for 1 year ago. But 1 year ago was 2 years past 3 years ago. So we're trying to find the initial amount of fish 3 years ago. So 1 year ago was only 2 years removed from 3 years ago. So 2 should be the input for x. And then that gives us the expression 30 equals CE to the K times 2. 3 years ago, the initial time is 0. We were also told that there's 150 fish now. Okay, so 150 is the y value for now, but now is 3 years past 3 years ago. So x should be 3 for now, x should be 2 for 1 year ago. So that gives us these two equations. Okay, so again, 1 year ago, x is 2, now x is 3. And 1 year ago, the y, or the amount of fish, was 30. Now the y, the amount of fish, is 150. So the first equation I could rewrite by dividing both sides by e to the 2k, and that gives me an expression equal to c. I could then take that expression and plug it into the second equation, because the c is the same in both of the equations. When I do that, notice that I get e to the 3k being divided by e to the 2k. So the e to the 3k divided by e to the 2k leaves me with e to the 1 times k. So my original equation can be cleaned up to be 150 equals 30 e to the k, and we'll be able to solve that for k. So solving our cleaned up combined equation for k, divide both sides by 30, and 150 divided by 30 is 5. We want 5 to equal e to the k. Use the inverse function natural log. So plug both sides of the equation into the function natural log. So 5 is getting plugged into the function natural log. E to the k is getting plugged into the function natural log. And natural log and e to the k cancel each other out, leaving just k. And natural log of 5 is a number. It's approximately 1.609. So now that we have solved for k, we can put that into the equation 30 equals c times e to the k times 2. So notice k can become natural log of 5. I'm going to write it in an exact form, natural log of 5. It is approximately 1.609. This will allow us to solve for the c, because e to the natural log of 5 times 2 is a number, and I can divide both sides by that number, leaving me c. So c is equivalent to 30 divided by e to the natural log of 5 times 2. Now here I've shown us using a rule of logarithms. We will talk about the rules of logarithms in a different section, but 2 times natural log of 5 is equivalent to natural log of 5 squared. And e and natural log are inverse functions, so they cancel each other out. And so the e to the natural log of 5 squared is equivalent to 5 squared, which is 25. 30 divided by 25 is 1.2. So the initial amount of fish is, yeah, again, these are averages, so that's why you're getting a 1.2. So the initial amount of fish 3 years ago was only, 1 fish. There was probably a second fish consumed. So anyway, that's our estimate for the initial amount of fish from 3 years ago. So we have solved for our exponential model that is modeling the growth of the population of these fish. The leading coefficient is 1.2 and the k was 1.609. So 3 years ago there was approximately 1.2 fish in the stream, and the population was growing continuously at a rate of 160.9%. That's what 1.609 is if you turn it into a percent, 160.9%. In 3 more years, that will be 6 years from the initial beginning of the study. So in 3 more years, x should be 6. So put 6 in for x and do the calculation on your calculator, and you get approximately 18,700 steak and fish in that stream system. Populations usually taper off in growth after an initial exponential growth, and the resulting pattern kind of looks like an S shape, so sometimes people call it the S curve, but its actual name is a logistic curve or logistic pattern. So again, growth usually starts off a little bit slowly and then it picks up rapidly. And so the graph is very steep in the middle, and then it starts to taper off, and thus giving you kind of an S shape. Again, that's called a logistic curve. Most populations usually eventually follow that trend.